So we met friction last lesson, and we discussed this magic quality it had, whereby it knew which way it had to work. It always worked in the opposite direction to the way something was either moving or the way it wanted to move. So even though it wasn't yet moving, friction knows which way it needs to act to oppose it. There are two scenarios that we deal with friction. There's the scenario where something isn't yet moving, and in that case, friction is exactly matching whatever force is trying to make it move. And then you reach the point that we referred to as limiting equilibrium, where friction reaches its maximum value. And that maximum value, sometimes referred to as F lim, but generally these days referred to as F max, is equal to the coefficient of friction, which we use the Greek letter mu for, multiplied by R, which is the reaction force pushing up on whatever object it is from below. And so if something is moving, we know friction has reached that value, and it doesn't get any bigger than that. So you've got to look carefully at questions and ask yourself, are we dealing with a situation where something is yet to move? Or are we dealing with a situation where something is either about to move, limiting equilibrium, or already moving? And in this case, we've got something which is already moving. It's sliding down the slope. So go on, see if you can sketch what are we talking about? A particle. See if you can sketch the forces that are at play in that scenario, okay? Including friction. There may be some more in there. There's two, so we've only got those. I don't know where they're. Okay, so there's no extra forces involved. The only thing making this particle slide down the slope is its weight, and those are the only forces involved here. We've got the weight of the particle, we've got the reaction force. The weight is vertical, the reaction force is perpendicular to the surface, and then we've got friction, which is opposing that movement, because this is accelerating down the slope at 0.25 meters per second squared, so we know friction is opposing that motion. Let's fill in the angles. So we've got a 15-degree angle here, so I know that angle there is 15 degrees, and this angle here is 90 minus 15, which I'm relatively sure is 75. And you might think, well, I only need to resolve parallel to the slope, and that's movement involved, so that's F equals ma. But we're asked to find the coefficient of friction, so we do need to know R. So as well as resolving parallel to the slope, we need to resolve perpendicular to the slope, because that will allow us to work out R. In fact, that's where I'm going to start. I'm going to resolve perpendicular to the slope. I don't need to worry about friction. I've just got R going up and the component of the weight going down. Remember, we're not working vertically, we are resolving perpendicular to the slope. Let me give you a minute to see if you can get somewhere with that. So I resolved perpendicular to the slope, that's not F equals ma, that's just equilibrium, up equals down. R pointing up, and the component of the 0.5 g weight pulling down. So that's 0.5 times the cos of the angle. If you put sine 75, fine. So that's the value of the reaction force. So that multiplied by mu is the maximum value of friction, which we know is in effect here because this thing's already moving. I didn't bother working it out because I know it's going to be a horrible number. So I moved here now to resolving parallels to the slope, and I had F equals ma then because it was moving. So I said down the slope was positive. So the force pulling it down the slope is the component of that, 0.5 g times the cos of 75. That's being held back though by friction, and that's equal to mass times acceleration. Friction is at its maximum value because it's already moving, so that's mu times r, which we've calculated over here. So mu times that value of r that we just calculated is the value of friction, and then it's just a little bit of jiggery pokery to rearrange that and get that correct. So there are a number of different ways this sort of question can be asked. You might know, in this case, the acceleration and be asked to work out the coefficient of friction. You might know the coefficient of friction and be asked to work out the acceleration. There's a number of ways this can be asked. So let's just do a little bit of practice. So page 104. So I'm up to 7 textbooks. So I think if there's 3 of you, 2 of you can share the textbook, and then I've given you a printout. But the person with the printout can look in the book for the answers. Ollie, you can either use a printout or make friends with Harrison and sit next to him. That's entirely up to you. So page 104, 5 and 6. So we've done 3 and 4 now on that page. And then I've said page 105, 4, 5, 6, 7. Is it a different exercise? Oh, it's the mixed exercise, right? Yes, sorry. There you go. So when you get to the page 105 questions, it's a little bit of everything there. It's the mixed exercise. So 4, 5, 6, and 7. Okay. Yes. So with number 5, we're going up the slope this time. So I've resolved perpendicular first, and you've got to be clear in your mind about the effect these forces are having. So if I'm moving in this direction here, there's only one force pushing up, and that's the reaction force, but there are now 2 forces pulling it down into the slope. You've got the weight like we had before, and the angle between the weight and that perpendicular line is 30, so that's 5g cos 30. But you've also got this force, and although it's pushing it up the slope, it does have a downward effect because the angle between that force and the perpendicular line is 60 degrees. So that's where that comes from. Now we're being asked to work out the value of P. So at the moment we can't get any further with that. I'm hoping that somewhere along the line we're going to work out the value of R, because that will allow me to rearrange that, but let's sit tight with that. We then go parallel with the slope, and again this time, because we're moving up, I'm going to say up is positive. And there's only one force pushing it up. It's the component of this force. Now the angle between that force and the direction we're talking about is 30. So I've got P cos 30. I've got 2 forces slowing it down. One is friction, and that's working in the direction of the slope, so no need for an angle there. And then you've got the weight, and the angle between the weight and the slope is 60 degrees. So that's both of those being taken away, and because it's moving, that we're in the world of F equals ma. Now, F I know can be calculated as mu r, and I know what mu is. We're told in the question. So I know that mu is 0.2. Remember, the coefficient of friction is always a number between 0 and 1. So in that previous question, if we'd got an answer of 3, we would have known we'd made a mistake. So I know that and again, we've got that situation, I did promise that to you, that we've got a lot of causes going on here, but we should be able to rearrange this equation to get what R equals. And that should allow us to substitute it into that equation and rearrange that to work out what P equals. Please make sure you use your memories on your calculator rather than using a rounded value from there in there. I'll give you a minute to finish that one off. Yeah, Hannah's pointed out that we've got P in both equations. So what we're going to do instead is we're going to take what R is equal to and we're going to put it in there, and that's going to give us a couple of P's. The only good news is that I forget whether it's cos of 30 or cos of 60, but one of them is a half. So it does sort of, it's not particularly nice, but it does fall out eventually. Right, so I used Hannah's excellent approach. There we go, plug that in there. And I then, having said avoid reaching for your calculator, I decided, right, I was going to reach for a calculator. I didn't actually need to, but because the cos of 30 isn't too horrible and the cos of 60 is a half, it didn't look as bad as I'd feared. This term is not particularly nice, but I'm going to let my calculator deal with it. I then multiplied out the bracket minus 0.2, and I know I'm using a mixture of decimals and fractions, but there we go, so be it. I then had 2 terms with a P in, so I've got to use my favourite rearranging trick. Moved those 2 things to the other side of the equal sign and then just factorised. And so P is equal to all of that divided by all of that. And again, my calculator did all that work for me. Yeah, I mean, A-level questions are hard, but that's stupidly hard, that one, sorry. I should have spotted that. So question 6 is the last sort of one from that exercise, and then there's just a mixture here. So when you get to these, just make sure you're reading the question carefully. Is it smooth? Is it rough? Is it moving? Is it about to move? Is it not yet anywhere near moving? Yeah, they're a bit of a mixture of everything we've done recently. I'd always start with a diagram and label up the angles.